All right, can everybody hear me okay? Okay. I need to make sure I'm recording this one because the other one I missed half of it, rushing between classes. So I did grade your oscilloscope quiz. Just a couple of things about it, just to be some of our tips. Number one is, a number of you folks, when you measured the signal, you had the scope set to DC. So, and I guess I'll change cameras here real quick. I'll show you. So on at the top of the, I need to give it a second for the camera to adjust. On the top of the scope, there's a switch, and you just need to set it to AC. Okay. When you set it to DC, it allows you to see both AC and DC signals. All right. So you just need to set it to AC. Okay. So that's one thing. Let me switch back. I noticed a lot of people pronounce the first C in the word oscilloscope as they did the video. You don't pronounce the first C. You just OS. You just think of it as OS, oscilloscope. Okay. Actually, it really doesn't. It doesn't affect the trace. It will if there is a DC component. It will actually shift everything up or down by a constant. So if you have a 1 volt DC component, then the AC voltage will go up by 1 volt or down by 1 volt, depending on how it's biased. The other thing too is when you're measuring either time or voltage, if you want to get as much precision as possible, you do want to stretch the signal out as much as possible. So if you're measuring time, let's say you have a signal that drops off very quickly, like this, and you want to measure the time it takes for the signal to go to half its maximum value. This distance on the scope, on the screen of the scope, is going to be probably less than 1 unit. And if your uncertainty is 0.1 out of 1 unit, you're automatically at 10% error. But if you stretch this out, so that maybe this takes maybe 2 units, wherever you can. I know you can't change the steepness, but but you can stretch this out a little bit. Maybe so this takes 2 units, or maybe 2.5 units, or whatever it is. Then you get a little bit more precision. Yeah, if you're you can have the window show less than the full cycle if you're measuring, especially if you're going to be measuring time. Obviously, if you're measuring the period, you got to probably see the full cycle. All right, if you're measuring the period of a signal, but if you're just measuring the time it takes for the signal to go from here to here, you don't need to see the full cycle. So on these scopes, if you press the first and second button twice, it allows you to adjust the trace vertically and horizontally. That's one thing. And then the other thing, you can just change the time base or the voltage base, so you can stretch the signal either vertically or horizontally. The other thing too is when you measure, let's say you're measuring time from this point, what you want to do is you want to shift this vertical line so that it's on one of the grids. You want to place the vertical line so that it's on one of the grids. That just makes it easier for making the measurement, because that'll be you can make it your starting point. So how do you do that? So if you press the button, let's say the second button, you press it twice, and you use the horse and you twist the knob, you will see your signal move. Okay, move horizontally. If you do the first button and press it twice, you'll move everything vertically. Let me go. I'm going to show you the other scope real quick. It has different settings, but oops. There's one thing on it I just want you to see. So when you look at, in your case it's yellow. In your case you have this thing that's yellow. That shows you how you're adjusting the time base. Not the time base, but it shows you how you're shifting the signal horizontally. So on yours, if you press the second button, yeah, no, the computer just told me my signal's bad. If you press the second button twice, and then you adjust this, you will see this marker move to the left or to the right, depending on which way you adjust the knob. And that will adjust the horizontal trace with it. Okay? If you press the first button twice on your scope, and you use the knob, this knob at the bottom, then it'll adjust the voltage up and down. So you can put the bottom of the signal with one of the horizontal lines. That could be your starting point for making a measurement. Those are some tips I'm giving you so that it makes it easier to make the measurements. And if you forget what I said here, if you read through the scope quiz, it's actually described in there. Okay. There's a series of like eight things that I described in there regarding the scope. And if you need, I can resend that information. Are we okay with that? Am I still cutting up pretty bad?
Professor Calabrese, I have a question about the transient lab.
Yeah. Okay, so go ahead.
So for part one, it's just a really small question. For part one, it asks for you to measure the external resistance R. Is that asking for you to measure the resistance of the resistor in the circuit and recording that?
Yeah, you want to measure.
I just want to make sure that's what it's asking.
Yeah, you want to measure the resistance of that resistor.
Okay, cool. That's all. Thank you.
Are there other questions on the transient lab?
With the transient lab, part one with the capacitor, what's the sort of expected percent errors on them? Because I got a pretty good percent error. I got like 0% error almost for the 500 hertz, but I got pretty big percent errors for the 250 and 100 hertz. And I'm not sure what happened.
How big is the error? 100%?
I got like 0% for the 500, and then I got like 26% for the 250, and then 49% for the 100. And I followed the same procedure, so I'm not quite sure what happened.
Okay, so how many? I guess my question is, how many boxes wide was your delta T in each of those three cases?
Look at my pictures. for my 500 hertz, my delta T was like 2 boxes, and like 1 box. So they're a bit short, but none of them are crazy shorter than the other ones.
Well, I mean, that makes a big. I mean, the 49% error is troublesome.
Yeah, that's why I'm not sure what happened. Like I'll try it again, but
Can you
if
send me
it's not
this?
supposed to be that percent error, then I most likely did something wrong. So I'll try it again.
Can you send me screenshots of the traces? If you do it again, I mean.
Yeah, I don't know if I can send them like right now.
No. I mean, when you redo it.
Yeah. I'll redo it and I'll send the traces again.
And I can take a look at it over the weekend and see what the issues. I know that the second part, you're probably not going to get. It's probably going to be digital. It's either going to be 0 or 15% error in the second part in the Rl circuit.
It's going to be what?
You're either going to get 0% or 15%. When I was doing it, I got either one error or the other error because the signal drops out very quickly.
Yeah.
So I don't expect 0% error on this lab because you're measuring with the scope, especially with this scope. So I do expect more error in this. That's fine, especially as compared to the DC circuit lab, which people are getting like 0.1% error in a lot of the measurements. Well, yeah, I'll take a look at your traces and see.
Yeah. So with the traces for this lab, it's okay to not show like both peaks even of the trace necessarily. Is just sort of get the half-life time as big as you can to get as much accuracy as you can.
Yeah, that's ideal. That's what you want to do.
Okay.
Yeah, and for the second part, because of the fact that I had the value of RNL that I had, that it's very fast. It drops very fast. So to get really good results is difficult.
Yeah. Okay.
Are there other questions?
I just have one more question. So when I'm doing it and I have the whole thing set up and plugged in, my oscilloscope just shows a flat line. I'm assuming that the major issue for that would be it's just not wired correctly, right?
Yes.
Okay, so I'll just check that then. Thank you.
Yeah, just make sure that, you can put the scope across between the resistor and the inductor just to make sure that you're getting the power supply voltage.
Well, yeah. Well, so it's a resistor and a capacitor. It's just when I put the oscilloscope across the capacitor, it just shows flat. So I just want to make sure that like the main source of that would just be I didn't wire it correctly, and it wasn't like something else that I'm not thinking of.
Did you try it across the resistor?
No, I haven't. I'll try it across the resistor.
Okay. If it's still not working, let me know.
Okay, cool. Thank you.
Okay. When the scope I'm using, with 2 inputs, you have to be careful. You actually have to have your black side connected together. There's a common to them, but because you're only measuring one signal, I don't foresee that problem. But you might need to have the capacitor, one end of the capacitor ground.
Well, so I have the black end on black end and red end on red end. Like they're on the same side for the oscilloscope and for the signal generator. Is that what you mean?
Is the black end also connected to the capacitor?
The black and I mean both of them are, right? Because you want to connect your oscilloscope across the capacitor, correct?
Yes.
So they would both be connected, one to each end.
In other words, let me draw it on the screen. So you have like that,
Yeah, just like that. Yeah.
and then the scope. Like that?
Yeah, just like that. Yeah. Mm-hmm.
Not sure why it's not working.
That's how I have mine set.
Something's not connected right then.
Yeah, I'll reconnect everything. See, and if it doesn't work, I'll let you know.
Okay,
Thank you.
sure. Other questions?
The question for the analysis on part 1, where it's asking which value yields the poorest agreement, explaining why. I mean, my results were a bit off, but does that have to do with the frequency of the wave?
Yeah, I guess the
Or-
question is, does the frequency make a difference?
Okay.
Is the capacitor charging up to its maximum value? For example, let's say we did this lab at 5,000 hertz.
Yeah.
The capacitor would be
5,000
able to
hertz, you
charge
wouldn't
up.
expect the capacitor to charge up to its max.
So the higher frequency, you would
It's all
expect
different.
the worst results, right?
Yeah.
Okay, in that sense.
Okay. So. Okay.
Yeah, so that's an issue too, right? So the one question about the poor data at the higher frequency, it's kind of bothersome to me. There's typically if the frequency is higher, then the capacitor won't charge up, won't have a chance to charge up. You might not even get up to halfway. Yeah, if you're like at 5,000 hertz, for example.
Okay. And then for the second part of the lab, what is it? Not the resistor, the inductor.
Yeah.
That's the brown one, right? Like the thick.
It's the brown one. It's a big brown one.
Yeah.
Here, I can show it to you real quick. I want to make sure that you have it. I had it hooked up in a circuit, but I'm going to disconnect from the circuit. You see that big one?
Yeah.
That's the one. It looks like you would think it has the same color code as a 1,000 ohm resistor, but it's not. It's 1,000 microhenries. And what we did for next semester, we tried to get different inductors so it's not confusing for the students. Other questions? No concerns about the transient lab? I mean, I will have office hours on Monday. I won't have office hours tomorrow. Okay. This is Turkey Day. But if you do need to set up a Zoom meeting, I can always do something on Friday if I need to, or Sunday. If there's a problem and you need to discuss something with me, I can always set up a Zoom meeting with you, either Friday or Sunday, if that's okay. If that works out for you. No more questions? Okay, so I want to talk about our last lab of the semester. I kind of wanted you guys to turn in. I know some of the ones that are due are kind of pushed together. A part of it is because I want you to spend time on this last lab. Normally, it's our capstone lab. I've taken several parts out of the lab because of the scope you're using. We weren't able to get you the scope that you see on the screen now. So when you see this RLC circuit, one thing you can see is, and I'm going to change the frequency up in these RLC circuit. Maybe I'll blow up the picture. This is the RLC circuit, and I have the inductor set to 10 millihenries. I'm going to change the frequency. So right now the inductor is dominating. In other words, the voltage across the resistor is ahead of the voltage across the power supply. Now I'm going to decrease the frequency. You're going to see the voltage across the resistor get bigger and the phase shift get smaller. So I started at 6,300 hertz, now I'm at 3,800 hertz. And slowly the phase shift keeps getting smaller and smaller. Of course, everything's getting wider and wider. I'm at 1,900 hertz, 1,800, 1,700. Look at that. At around, it's basically between 1,500 and 1,600. Notice that they're in phase. This is approximately the location of the resonance frequency. And so if I go below that, and I got to change scale, if I go below that, you will see now the phase shift become negative and the capacitor dominates here. And as the capacitor, the effect of the capacitor becomes more important or more significant, then the voltage across the resistor you can see gets smaller and smaller. So what we're going to do in our last lab is analyze the circuit. And there's quite a bit of analysis you have to do, and there's quite a bit of data taking you have to do. And there's some planning you have to do this lab. Okay? There is some planning you're going to have to do. So let me draw the circuit. And we'll talk about it. You won't be using the scope to make measurements across the resistor and capacitor just because you really need to compare. You need to compare it to the power supply voltage. Otherwise, it's not of much use. You really need a two-channel scope. So let me draw my RLC circuit. It doesn't matter here what order I draw them in, okay? And what you're going to do in this lab, you're going to measure the current. So we got to put an ammeter here. And because we're using the multimeters, ideally, if you had five multimeters, you'd be using all of them for this lab. When we do this on campus, we set up 5 multimeters. One to measure the current, one to measure the voltage across this guy, one to measure voltage across the capacitor, one to measure voltage across the resistor, and one to monitor the power supply voltage. And then you also have a scope hooked up across the power supply voltage and the resistor. So there's a lot of instrumentation that's used when we do the experiment on campus. We can't do that because this experiment would be very expensive. And then you're going to monitor the power supply voltage of the scope. And when I did the lab over the summer, I noticed that the digital readout, it's a little bit inaccurate. So when you're monitoring the voltage of the power supply with the scope, go by either the peak-to-peak voltage or the amplitude. I would just use the peak-to-peak voltage to make sure it stays the same. Okay, just make sure it stays the same. Because it will vary as you change the frequency. All right, and I should say as a function. Our goal is to get a nice plot of IRMS as a function of omega. And you'll see a picture in the lab where this is frequency. I prefer that you plot it as a function of omega because you will be doing the curve fit on this, and you have to plot I versus omega. And you'll do a curve fit I versus omega. It'll make it easier for you. If you plot I versus F, then you're going to define an equation. You're going to put 2 pi's everywhere. It makes the equation very cumbersome. So your goal is to get this graph. And the graph is really asymmetric. As R gets bigger, the graph is asymmetric. You got to do a little bit of preparation beforehand in order to do this lab. So first of all, you want to measure the capacitance of your capacitor. You're able to measure C. Measure it. Okay, this multimeter can measure C. The one I had over the summer could not. But since you're in a position to measure it, you should measure it instead of writing the 4.7 microfarads. To measure C. Now the inductor, you're going to be using, you only have one inductor in your kit, so your inductor L is 1.0 millihenries. And just as a reminder, again, that's the inductor, that big one. Okay? And I should show you the resistor that you're going to be using too. The resistor is about a 1.2 ohm resistor. It's this guy. It's gray. It has a gray body. Okay? This is the resistor you'll be using. Okay? So we can't measure it. It's 1.0 millihenries, okay? I would calculate the resonance frequency. Then I would set up your circuit and measure the current at the resonance frequency. Then you might be thinking, okay, what voltage should I set it to? I left that kind of open. I let the voltage, I left it open. And the reason why is because you guys might have gotten a slightly different version of the signal generator, which I'll show you here. Than I do. Okay? And by the way, a couple of people pointed out that the plug on the signal generator doesn't go all the way in. I know it's a weird flaw, but that's how it is. Okay. When I did the lab over the summer, I was limited to 25 milliamps, but the manual implies 250 milliamps, which doesn't make sense to me. I can only go to 25 milliamps. So I left the voltage open to you. Okay. So if you can get more than 25 milliamps out of this thing, that'd be great. So you want to set this to the resonance frequency. You want to set this to the resonance frequency, measure your current, and see how big a current you can have this thing supply. Okay. If you turn this up, if you turn the knob up and the current doesn't change, that means you've pegged the power supply. You reach the limit. But if you keep turning this up and nothing changes, that means that you've hit the current limit. And you want to go below that. If you look at the scope will look like, if you look at the signal on the scope, it will look like this. Which is what you don't want, okay? You don't want to peg it. You don't want it to cut off. You want to be below the cutoff. I would hope, I really what I would like for you is to have the current to be above 25 milliamps. Why do I want that? Well, the resistor is 1.2 ohms. I measured it. At least my resistor is 1.2 ohms. Okay. If your current is going to be below 25 milliamps, actually, you really want it to be above 20 milliamps. If your current is going to be above 20 milliamps or below 20 milliamps, then you're going to be using this on a 20 milliamp scale, and then the resistance on the 20 milliamp scale is significant, and it's going to affect your circuit. That's why I'd like to be in the next high scale, but if we can't be in the next high scale, that's fine. We'll use a 20 milliamp scale. Okay. Ideally, I would like for you to use a 200 milliamp scale. So set the circuit up at the resonance frequency, and hopefully you can get a current above 25 milliamps, 20 milliamps. Let's say above 20 milliamps. Okay. So you can use a 200 milliamp scale. Once you reach, once you find your IM and you set your scale on the meter, do not ever change the scale of the meter during the entire experiment. Do not change the meter scale during the entire experiment. Okay, so what you might want to do ahead of time is find the maximum current, or you will define the maximum current and see how the current ranges from the low frequencies to the higher frequencies. That'll give you an idea of the range you should have to set this meter. You want to use the big meter. Okay? This will be measuring current. That's what this one is. Is that okay, Morgan? If you change the scale, you change the resistance of your circuit. Because remember, the resistor is 1 ohm. And on the 20 milliamp scale, this is, I forget what the value is, it's significant. Okay. Even at the 200 milliamp scale, you probably notice it too. If you were on a 10 amp scale, that'd be great, but if you're on a 10 amp scale, you're going to have very few sig figs. Oh yeah, it makes a significant difference because the resistor you have in the circuit is 1 ohm. It makes a big difference. And in fact, well, I don't want to say anything else. I don't want to say anything else after that. Okay. But the meter does have resistance. And so, yeah, it makes a big enough difference just because we're using 1 ohm now. You might be saying, well, why the heck did he choose a 1 ohm resistor? That's crazy, right? I mean, you might be thinking that. And the reason why I wanted to use a 1 ohm resistor is because I wanted to make this peak as narrow as possible. I wanted you to see the resonance peak. And the width is going to be narrow enough. You might get the best value you probably get for Q is about 10. I was trying to get you to have the Q value to be around 10, but it's probably going to be less than 10. When you do a similar experiment in Physics 215, you're not going to do it in 215 next semester, period 215 next semester. We do it a driven damped harmonic oscillator, the math is the same. Q is about 200. When we do the driven damped harmonic oscillator, the graph is like this. Of course, it's very hard to pin this peak down when it's that sharp. That's why I chose 1 ohm. Because otherwise, if I chose like 50 ohms, this thing will almost be a flat line. Okay. So that tells you why I'm using the 1 ohm and then why the meter affects it. Okay, so the meter is going to play a big role here. Either way, you'll see the role played by the meter. And maybe something else. Okay. Our goal is to pin this graph down. So you have already found F naught, you found your maximum current, and then you played around and tried to see what your current's going to be at the low end and at the high end. What range of frequencies should I scan? I probably wouldn't trust this meter above 5,000 hertz, although they don't tell you exactly what to trust it at. But I noticed that 1,500, 1,600 to 2,000, it was okay. Okay. If your resonance frequency is about 1,500 hertz, what range of frequency should I go to? You don't need to go to 5,000 hertz. Okay? You probably could go maybe 2,000, or maybe a little more than that, 2,200 max, if this is the peak. And maybe this is 300 to 500. You don't want to scan a huge range. And so the next question is, what should your step size be? Should I go 300 and 400 and 500 and 600 and 700? And I'm going to say no. Your step size has to change. Why does your step size have to change? You're right, the slope isn't constant. I want to figure out, I want to really get a good feeling for what this peak looks like. So I'm going to get more points here. I want more points, my density of points will be greater around the peak than when I'm way out here. If I'm way out here towards the ends, I can take steps of 200 to 300 hertz. But up here, I want to make the steps as small as possible. Yeah, I want an accurate graph. That's right, Morgan. You want an accurate graph. But so I need the steps to be small as possible here. And you can make them big here. You can make them 200, 300, 400. Probably on this side, you can probably go up to 400 hertz steps. But you want to get a lot of points here. You want to be able to see that peak just from the dots of your data, from your graph, from your data points. Yeah, just from the dots from your data points, you want to be able to see the peak. Then when you do a curve fit, you will be able to get a good curve fit. I said in the lab, you want a minimum of 25 points. I've had some folks go crazy in the past. They've taken as many as 80 to 100 points. That's probably a little excessive. Okay, you don't need that many data points. But let's talk about the peak here. You want to pin that peak down. So with the signal generator, you can take steps of 1 hertz. Do you want to take steps of 1 hertz up here? Well, how do you measure C? The multimeter. Sorry. You want to know how you measure C? With the multimeter, there is a. You just connect the probes to the. Yeah, there's a Farad setting on it, which I was surprised because the one I had used over the summer did not. But this has a Farad setting on it. It's on this side. It's going to be too close, I think. It's right there. Maybe a little bit blurry. Okay. All right. So, going back to this question about 1 hertz steps, if you go by 1 hertz at a time and the current doesn't change in the multimeter, then that step size is too small. Okay? The smallest step size should correspond to how much the meter reading changes. If the meter reading doesn't change at all when you change the frequency, then your step size is too small. Maybe 5 hertz will work near the peak. Okay, maybe a 5 hertz step size. You notice that, here maybe a smaller step size will work, but the graph is kind of at the peak. The slope is 0, so doing a one hertz step size might not work. So you have to think about that. You have to think about what you're doing. And one thing I said to the other group was, we don't make, the department in general doesn't make the labs like cookbook type labs, because the idea is for you to think about what you're doing and not just go through the motions. Okay, because you don't learn anything doing that. So we need you to think about what's going to work best for you to collect the data. And you just got to play around. Look at what happens when you take 1 hertz step size, 5 hertz step size, 10 hertz step size. Okay? Does that make sense? So you want to get this. This is the only plot you'll be making that does a curve fit. Okay, that requires a curve fit. The other plots, the other 5 plots, don't require a curve fit. So once you've done all that, once you've planned it out, then all you got to do is take the measurements, vary the frequency, and make the measurements. So you got to plan a little bit, and then just take the measurements. It should go pretty quick. And I'll be honest, it takes a little bit longer in the online version, because you only have 1 multimeter, so you got to move it from here to here to here. When we do it in class, you have 5 multimeters. Okay, everything's in front of you, so you can just change the frequency and everything. You just got to read the meters. Here, this takes a little bit more work on your part. And then when we do it on ground, we use the scope. You actually measure the phase shift between those 2 signals. I'm not having you do that because you can't do it. So the other version of the lab is much longer. So the graphs you're going to be making, let me show you the graphs you'll be making. The last page has samples of the graphs. Those are the graphs you'll be plotting. So the first one on the left is just a plot of x, z, and x sub c, x sub l, and z is a function of frequency. So we're going to calculate those, and I'll show you the calculation for them. And then this third graph here is going to be v sub l and v sub c is a function of frequency. So the bottom graph and the one on the top left, you can just plot them as a function of frequency. But the one on the top right, I would plot as a function of omega. So when you graph the one on the top left and the one on the bottom, do not connect the data points. Because if you're using graphical analysis, it's just going to look like a jagged line. Some professional software, they'll do something called a cubic spline fit, which will actually smooth that thing out, which is smooth it out a lot. Cy Davis will do that. But I don't expect you to do the line. I don't want you to connect the lines. Okay. Or connect the dots. Okay. You should have enough data points to be able to see the trends. So when you're plotting multiple plots on one graph, please use different colors. And you probably want to have a legend. And for the top graph and the bottom graphs, you're going to be reading information from the graph. So there's no curve fitting that's required. It's the current graph that we're going to be doing the curve fit. So before I talk about doing the curve fit, I need to talk about all the calculations you'll be doing. I put a sample data table in here. So you're going to have the frequency here, omega here, V sub L here. So let me tell you the quantities you're going to calculate. You'll be calculating X sub L. You'll be calculating L. Oh, you're going to be calculating omega. You will be calculating X sub C. You will be calculating C. And you will be calculating Z. And you're going to have at least 25 data points. So if you do this in a calculator, you've got to use the calculator at least 150 times. And I don't want you to do that. Scientists don't do that. Scientists use Excel. They use spreadsheets. So I want you to use a spreadsheet to do the calculations. So some of you folks already know how to use a spreadsheet. Some of you guys don't. Why are we calculating? We want to see if the value of L that you calculated matches what it says on the on L. Same thing with C. We want to see how it matches. Because the value that you obtain from the data matches what you measured with. Yeah, we do. We're also going to get omega naught from these values too. We're also going to get omega naught from the curve fit. You want to compare. And in fact, let me go down and you'll get omega naught from your curve fit. So you're going to calculate omega from here, compare. Okay. You're also going to get it from the graph. So remember, that 1.0 millihenries is just what's given, right? It's just a number. It's given to us, but we don't know how precise that is. And we don't have a meter to measure it. So we want to see if we can get it from a experimental measurement. Okay, I'm going to copy this data table. And I'm going to go into Excel. Hold on a second. I got to create I want to get rid of the one from the previous class. And I got to switch views again. Not that one. This one. Okay. So I'm going to go in Excel and I'm going to paste. I copied the data table. I'm going to hit paste. So there's the data table. Let me blow this up. So let's say we have some frequency value, 100. Hit return, 200. If I went 100 at a time, I can highlight these two rows, these two cells, and just drag the right-hand corner downward, and I have all the values. Now, I want to calculate omega in this, so I'm going to blow this up a little bit. So to calculate omega, I'm going to hit equal, and I'm going to hit 2 star, capital P-I with open and close parentheses, star, cell A5, 5, and hit return. And it gives me the value of omega. Let me make the windows smaller. I'm going to highlight the cell, go to the bottom right-hand corner, and just drag downward. How well do I know the frequencies? Probably to 1 hertz. So maybe in this column heading, I should probably say ±1 hertz. So that tells the reader that these are all within 1 hertz. Now, these angular frequencies, what's wrong with them? Yeah, it's way too many decimal places. But in fact, if these are all to +1 hertz, then these values should be no more than 3 sig figs. So I'm going to click on this. I'm going to highlight these, and I'm going to go to Format, Cells, and oh, it doesn't show. That is strange. It doesn't show that window. That's very bizarre. Okay. This is annoying that I have to do it this way, but I hit Format Cell, and then I hit Scientific. And let me go back. But it's scientific with 2 decimal points. So all these values now have 3 sig figs. Because all the values in the first column are 3 sig figs. All these values have to be 3 sig figs. So I changed those. I didn't change the first one. I should have changed the first one. Okay? Let me change the first one real quick. And yeah, the formatting, I don't like that formatting e to the +2, e to the +3, but cannot help it with Excel. That's what Excel does. It is what it is. I gotta live with that. Okay? If you were writing something formally, like in a publication, you would have to change all that. You would not copy the Excel spreadsheet into the publication. Okay, you would have to fix that. The other thing you can do, you can actually put in here times 10 to the second, and then just put these numbers in, and just put times 10 to the second. Okay. So let me put some voltage values in. Let me fix that. Let me put some current values in. And I want to calculate X sub L. X sub L is the voltage. I'm going to hit equal, and then I'm going to type cell C5, because that's the voltage across the inductor, divided by the current through the inductor, which is E5. It gives me the current. I'm sorry, the reactance. Sorry, I get that. Interesting to see when you do this in the lab. It'd be interesting to see if there's any trends when you calculate X sub L and X sub C. Be interesting to see if there's any trends. Look for trends. And what is the trends? What do the trends mean? Okay. And then you can get L, because L, you're going to take X sub L divided by omega. So in this column, you'll do that calculation. Similarly, you can take V sub C over I and do this calculation, etc. And Z is just V sub S over I. You're going to calculate all this stuff. And then you can make the graphs in your Word document. Right, then you can create these graphs. So, for the first two, for the graph on the top left and on the bottom, it really doesn't matter what software you use because you're not doing a curve fit. But this one on the top right, you have to use a curve fit software that does a curve fit and shows you the curve fit results. By the way, if you don't know how to add rows, you hit return. So you put your cursor at the end of a row and you hit return, and it adds a row. What am I doing wrong with what's wrong with my table right now? What's wrong with my table? Yeah, it's on two different pages. So what you want to do is put the table on one page. So you have to keep hitting return. That's what happened in one group. I remember a long time ago, they had like a ridiculous number of data points, so their table went over through 2 pages. It was amazing how much data they took. You don't have to do that. Okay, so let's talk about the curve fit. Oh, is there a column for V sub S? That's going to be fixed, so yeah, and that's something you want to measure. You can measure that with a meter. And you will use the scope to just make sure that it stays constant. Because you can't use, because you got to be using that second multimeter to measure the other voltages. So you can use the scope to keep that constant. So you use the scope to keep the peak-to-peak voltage constant, but then you can use the meter just to measure the RMS value. Okay? And we're assuming that's going to stay constant. That's why you're monitoring it with the scope. Ideally, you want to monitor it with the multimeter, but that thing is going to be used so much it's going to be a pain. I also wanted to use the scope, that's why I'm having to do it that way. Okay, let's talk about the graph. The equation for the current is in your PowerPoint notes, but the graph of I, RMS versus omega kind of looks like this. It's asymmetric about the peak because of the resistance, there. Okay. When this is narrower, it actually looks a little bit more symmetric. But V looks like this. I'm sorry, I looks like this. All right, here RMS. That's what I looks like. And so you're going to plot this graph, and then you're going to do a curve fit using this equation. So if you're using graphical analysis, it doesn't have this equation. And you have the opportunity to do a curve fit with 1, 2, 3, 4 parameters. Don't use 4 parameters, okay? There's too many parameters. And it'll take you, you'll be surprised how long it takes for, if you use graphical analysis will take a while to do that curve fit. Okay. All right, so I would choose 3 fitting parameters. My guess would be this value, and this value I would make as a fitting parameter. By the time you're done with the lab, you will have a pretty good idea what L is. The reason why I worry about the measured value of R, because when you take if you take the multimeter and you just connect the wires together, it'll say like 0.3 or something. And this is like when I measured my resistance, 1.2 ohms. Okay, or 1.4 ohms, I forget what it was. Okay, so I'm not probably 100% sure of the value of it, but I probably have more confidence in this value from the experiment. So I would not use this as a fitting parameter. So these are my fitting parameters. If you want to, you can make this a fitting parameter too. And then, I'm sorry, you can make this a fixed value and make these 3 fitting parameters. I'm going to leave it open to you. And you can experiment. Okay. So you have to define a curve fit in graphical analysis or in Davis. Davis has a curve fit similar to this, except that it's really more for power, not for current. I'm having to do the current fit. So if you're in graphical analysis, you make this a fitting parameter, this a fitting parameter, that a fitting parameter. What you got to do is say, I'm going to call V A. Let me use a different color. You know, you got to type it, and it doesn't be a pain to type out. So you probably might want to type it out in Word, because if you do this in graphical analysis and you screw it up, you got to retype the whole thing again. But if you type it in Word, as you can copy it, you can fix it in Word and then paste it into graphical analysis. Or in Davis. This is why I said to use omega, not to plot versus omega, not F, because if you're plotting versus F, everything here would have a 2 pi, another. You'd have 2 pi's everywhere. So this is going to be a fitting parameter. I'll just call it B. These are the caret symbols. Okay, I said, let's say we got a value of, I'm making this up, okay? That's what you're going to have to type out. So you're going to hit the in graphical analysis, you hit define, fit, and then you got to type this mess out. So like I said, I would type it in Microsoft Word and then copy it and paste it, because if something's typed wrong, you got to type everything from scratch. Remember, these are caret symbols. And really same thing if you're using psi datas. What is B? That's this guy. This is the thing, so I'm letting this be B. Right, and X is omega. This is B squared times X squared, which is this term. Right? I mean, when you type, when you square something in graphical analysis, you got to type it like this. Whatever that, we call it the caret symbol or whatever. This is times, so this. So you have to use the asterisk for multiplying. That's what this is. And this represents this. Oh, this guy? This is the inductance. I'm assuming I know this value, and I'm squaring it. Yeah, I ran out of space. So there should be a squared here. I ran out of space. My board, maybe I should write it up. Let me write it up on top of this. I'll write it up on top because this board, the top board is bigger. And I screwed up here. There should be an asterisk here. This is why I'm telling you to type it in Microsoft Word. I hope I didn't forget anything. That better? Yeah, I would, like I said, no more than 3 fitting parameters. Because then you would have a fourth one. It makes it, the more fitting parameters you have, the harder it is. So the mean value of L that you get is the one you should use. Okay, but like I said, if you have confidence in the value of V, then put V here and make that a fitting parameter. I'm going to leave that open to you. But all I'm saying is don't use 4 fitting parameters. It's too many. I've had some students just use 2 fitting parameters and they work fine. So sometimes when you have these terms that are squared, sometimes the software will take the square root of that, and just report a negative number. I don't know why. Right? Because when you square a number, whether it's the number is negative or positive, you get a positive value. And sometimes for this term or this term, the computer will spit out a negative value. Just take the absolute value of that number. Okay? Just take the absolute value of that number. Are we okay? So that curve fit is going to be, I mean, it'll take a little doing. That's going to be the, take a little bit of doing, but it's going to give you your omega naught, and then you can compare, and you can get F naught, you can get F naught from that. You divide this by 2 pi, and you get the frequency, and you compare it to what you got, compared to what you calculated. Okay. If you did a good job in collecting the data over the peak, you'll get a good number. And it's much easier for you guys to do this than when the people do this in 215. They make a similar graph. The problem is, the people who do this in 215, the peak is so sharp, you can hardly get any data point. Maybe you get 3 data points over the peak. Whereas you're going to get a whole bunch over the peak. So you can actually pin that peak down beautifully in this lab. It's much more difficult in physics 215. Because their Q is like 200. Your Q is going to be probably less than 10. And if you're going to be taking 215 next semester, you won't be doing that lab because you can only do that lab on campus. That one's impossible to do at home. The equipment would be very expensive. You guys all signed up for 215? Okay, good. You'll have fun in 215. It's a cool class, especially if it gets to modern physics. Okay, so I did. So one of the issues I'm running into right now is I'm a little bit behind, and what I'm thinking of is I'm gonna go through and create a video where I solve. Oh, you're leaving Sarah. That's sad. That's too. Going to a 4-year school. Transferring already, Pedro? Well, that's good. That's a good thing, then. I know it's a sad to leave Sierra College, but it's a good thing. You're moving on to the 4-year school. And a lot of students do miss Sierra College when they transfer. That's true. It's a different environment, but you'll do fine. I think what I'm going to do is, because I was going to do a presentation on how I solve the equation for this system. I would solve the differential equation, and I really need the time to catch up. I'm desperately behind. I need to have some time to do some relativity. And so I think what I'm going to do is create a video for you guys to watch. And so Monday we have an exam. So I'm going to give you a practice test. I'm going to email you a practice test. Then Wednesday in lab and in lecture, in both the lab and lecture, I'm just going to lecture on material. Okay? And then next Monday, I'll also lecture. So that should give me some time to do some relativity. Okay? That way I can put at least 2 problems on the last test. So I'm going to do that. So I'll make a video on the solution of this differential equation. And in fact, there's a theoretical calculation you have to do in the lab. And so I have to set that up for you. Usually I go through the whole thing. I have to actually go through that for you in the video. So I'll create a video that you'll need to watch for the last lab lecture that I'll do. Okay? And I just thought of it now because I didn't even get to the beginning of chapter 34 with you guys. All right, so if I don't see you at 2 210R. Have a nice Thanksgiving.